Okay, so I think in theory you can get your Gadget 1 board right now. It's in the REL. I think a bunch of you already have. The stencils are here now, and we're going to get more paste. I guess we ran out of paste, so we'll order paste today. It'll probably be here tomorrow for office hours. So we'll have that done. So you guys can sort of do your boards. I think the office hours have been expanded or completed. I believe we posted that.
Yeah, an email should have gone out. Everyone should have gotten it. If office hours on Thursday and Friday.
But essentially, your Gadget 1, you can basically put together the same way as your mini Gadget. You got tweezers, you got parts, you stick them on the gooey paste, and then you can put them on the griddle. If you watched us do the griddling, it wasn't very complicated. It's not too much to screw up other than don't let your board sit on there so long that all the parts turn gold. That's bad. But maybe not completely bad. So today we're going to talk about Gadget 2, which gets digital communications. But first, while cobbling together your library, I missed on a part. And if you're using a BCD to 7-segment display and the 7-segment displays, you're going to have to do a part substitution. Or your board is going to do this cool thing where every time you want to see a number, it's going to give you the opposite digits of the number you want to see.
So only like the segments that aren't in your number, which is
probably not what you want. And that's our fault. We're sorry. We're going to order replacement LEDs. I'm going to order just all the red ones because I think we told you to do red. If there's some reason why that's not good enough, let us know. And they'll probably come tomorrow as well. So if you already soldered your LEDs, the best way to get them out is to use the hot air rework station in the REL. Get help if you don't know how to use it, but you basically just heat it up with the hot air and the part will just fall out. But it's much better than trying to desolder each pin individually. And then super fun details, we're going to have to cut any of the VCC traces that go to the CA pins. And then we're going to have to sort of mentally substitute CC instead of CA on those pins and tie them to ground instead.
So it'll be a little bit of fun.
Little jumper, and anytime someone asks you, you can say, yeah, our instructor is screwed up. That's not my fault. That should be fine.
How many people are using the display?
Surprising number. There's probably 5 or 7.
You have 2?
Yeah.
All right, did you solder both in?
No.
Good.
So just for completeness, when we play with DCDs in the future, we're going to use this other chip, which totally doesn't look like the CD4511. It's the 4543, which actually has one of the I/O lines, which lets you select whether you're using common anode or common cathode chips. But the pinout is completely different, and it's much easier to cut one trace on your 7 segments than it's going to be to rewire like 10 traces on a little tiny IC. Which is sort of the downside of surface mount technology. When you say rework, if you have like giant dip switches or wire wrap boards, you just change which your wire wrap it. But here you have your jump over the wires. So we're going to reorder those. Get them. Yep.
What do you mean by LEDs wrong or something?
So if you have 7-segment displays,
7-segment LEDs. So the display module, which contains the numbered LEDs,
yeah.
there's a replacement module which will work with the driver. We just have to switch this one line. That's all. If you have RGB LEDs or other LEDs, this has nothing to do with that. You're totally fine.
Yeah.
This is just for the
those are much easier
number
to fix.
display.
If an LED part was wrong in a library, we would just tell you to solder the 2 legs to the other one. That's much easier to fix. These are a little more annoying. So sorry about that. We'll get them ordered. We'll have the solder paste tomorrow, so you guys can continue with your Gadget 1. But just to start talking about Gadget 2, since this is a semester, we compress everything, keep you guys busy. And everyone loves it when the classes get more and more work towards the end of the semester, so we're going to do that. So just, first of all, what we want you to do is have a good idea for Gadget 1, or Gadget 2.
As opposed to Gadget 1's idea.
Yeah. Well, I think we like your Gadget 1.
No, Gadget 1 actually.
So we're going to give you a couple themes, because sometimes themes are good. And then there's also build your own. So if you've been dying to make some sort of like reciprocating seesaw circuit.
Now's your chance.
You can do whatever you like.
Give you plenty of rope to hang yourselves. It'll be fun.
Yes. But just to sort of give you some other ideas of like useful things to build gadgets for. There's a couple that we'd like to point out. One, there's Quality of Life Technologies. It has a weird acronym, but it's sort of a high area of research. CMU and Pitt have a joint Quality of Life Technology Center. They do all kinds of really neat sensors and gizmos, basically designed to help people make their lives better. So some very specific things like a pedometer is a good example of a little tiny gadget that helps give you information. And if you've ever seen or played with a Fitbit, it's a little Bluetooth pedometer. You just keep it in your pocket. The only thing it displays is how many steps you've taken and like a happy face or a sad face if you've been lazy today. But then as soon as you go near a computer that has Bluetooth, it just slurps up the data, sends it to their server, and then you have like all this back-end server software that tells you very interesting things like, here's your day, you've been getting more active lately, here's less active. So it's a simple way to sort of get this data and then do something interesting with it. And so they're focused on how to get the data and do something interesting with it. But you could just get the data, like portable heart rate monitors, sleep EEGs. There's some neat stuff where they did actually just recording ambient sounds around, and like also a sleep EEG. And basically they could tell that like when the dishwasher kicked on or something, or the furnace kicked on, it was way too loud and their sleep got worse. Or like when the central air turned on, their sleep got worse, and it was something about like the air quality went down. So their sleep got worse, their breathing got more erratic. So like fix your central air system. And like these are the sort of weird things that only become apparent when you go out there and actually collect all this data and do interesting stuff with it. So, it's something to keep in mind, just how do you take sensors, how do you integrate sort of data logging into somebody's life in a way that helps them. And that's basically what your Gadget wants, where we're trying to get you to take some sort of ambient information, like temperature or light levels, and then like tell somebody about it, so they can do something about it. Another sort of theme that we kind of like, is educational gadgets. Fun things you can do to make things like the Makey, I think was a great example of just like not too complicated, but people could do all sorts of things with it. Like I want to get in a keyboard at home. That sounds like a great thing to just have in your kitchen. You either eat the banana or play a little tune. Why don't I have this? I don't know. Or like programmable robot kits, or toddler toys, but maybe just something that shakes and buzzes and does fun things, drives around.
Has some buttons, does some activities.
Vernier probes. Basically, there's all these kind of crazy probes that you can buy, like pH sensors, angle sensors, joint sensors, and you can do all kinds of educational stuff with them, just by taking some very specific thing, getting information about it, and then letting people do stuff with this. And if you wanted to actually get this, if you know anyone who teaches or like works with kids or anything like that, you just say, hey, what do you do? What do you wish you could do? And usually people have problems.
Science teachers are often looking for ways to demonstrate certain physical concepts, which can be made a lot easier with.
If you could add explosions to a high school physics class, like people will love you forever. You just have to do it in a safe and controlled manner. Sometimes, a little bit of sensing and electronics can make that more interesting. And just general environmental sensors. And we need a lot of this stuff. There's a lot of pushes. This is an educational academic research facility, and there's actually a lot of money coming in just to get like water and air quality monitors, soil and pH. You want to tell them about the?
Sure. So there's at least 3 or 4 different groups at CMU right now that are doing nothing but some form of environmental sensing. So there's a sensor web project where they're deploying sensor networks, which are basically just microcontrollers like the ones you guys have been using, and they put them in fields at different locations to monitor stuff like the temperature and humidity over time to figure out why crops are growing or not growing. I work on a project where we take really simple sensors and put them in water and monitor sort of, we put them on boats that drive around, and we monitor things like water flow and pollution and stuff to tell whether fish are healthy or things like that. And then there's another project which is doing air and water quality monitoring with simple microcontrollers. The idea there is that you put a little sensor into your well water and then get back, conductivity and temperature, and know if the well water is sort of safe to drink or if it could be harboring bacteria because it's been warm enough for that sort of thing. So these are all very simple sensors that using the same technology that you guys have access to with these projects, and they're actually an area of active research. There's active grants coming in where it's like, God, we really wish we knew what made crops grow and stuff like that. Only we could just put a bunch of little temperature sensors all over the ground, or a bunch of different light sensors, and see how much light this area of ground was getting over time. Then we would know how crops grow.
And basically that's what gadgets are good, is this divide where there are people who want to do this science, but they're unable to because the engineering hasn't been done. You cannot simply buy these little boxes, or you can, but they're like fantastically
Hundreds of dollars or
expensive.
thousands of dollars.
And when you say, I wish to put 7,000 of these sensors per acre as opposed to like 2, because I assure you there are places where they have 1 or 2 of these big boxes with big solar panels on some farm, and they're here and there, and it gives them more information. But what we're getting to is where you can say, well, you know what, these mini gadgets commonly cost $6 to make. Could I just have 1,000 of them and put them somewhere and have them all talk to each other and record all this data? And that's basically what people are working on right now, and you can do the same thing. You have some interesting things that you want to sense and try to get this data back. All the technologies are really coming down to all of these sensors. 10 years ago, all these sensors were $50 or more. Now you guys can get them for $5 or less. Some are still expensive.
pH is still kind of expensive.
Wireless communications used to be ridiculous. Now you can buy Zigbee, which has sort of been rebranded as Bluetooth 4.0 low energy. You can use Bluetooth, you can use Wi-Fi.
So the stuff we're talking about today with serial communication will basically let you use a module which can go to any type of network that you can think of. Basically, people make modules which go from serial to Bluetooth to Wi-Fi to 3G. If you wanted to have a little gadget which can connect directly to a cellular network with a SIM card. Like once you have sort of these pieces in place, basically for $10 you can sort of do whatever you want.
And this is where, for a lot of your gadgets, we're nagging you about how much power does it use, how long does it run off your batteries, are you using batteries or power supplies? This is the kind of stuff where it starts to matter. It's like, well, I'm going to have this little tiny battery, I'm going to throw it in a field, maybe I'll put this tiny solar cell that will kind of give it energy sometimes, maybe. We live in Pittsburgh, there's no sun. I think we're cloudier than Seattle. So if anyone ever asks you which is sunnier, Seattle or Pittsburgh, Seattle wins. We just have less rain. And that starts to matter. Like, how do you put your thing in sleep mode so you're not using any power and can actually run off a single battery for 3 months or 6 months, so that when they say, well, we're going to do a research study in this field for 4 months over the growing season, it'd be nice if we didn't have to replace the batteries halfway through. Because they will, right? They'll grab some, scientists who'll have to run around in their little ATV driving through these fields and replace all these batteries because they're not engineers. They don't know how to make anything. All they're trying to do is collect the data so they can do their science. Okay, so that's environmental sensors. Or you can do whatever you want.
Yeah, some of you had good ideas that were a little too complicated for Gadget 1, and well, now's your chance with Gadget 2. You can, make annoying things to hide in your room for your roommates to find. Whatever you want. You'll have access to a lot more stuff with this. We're not limiting you to a specific set of parts like we were with Gadget 1 largely, and you'll have access to serial communications and digital communications in general, which means that if you are able to find something on the market which does some complicated bit of stuff like Wi-Fi or 3G, you can drop that onto your module, and now you actually have a module which, for all rights and purposes is basically equivalent to something commercial in a lot of respects. So hopefully you guys have lots of secret great ideas that you've been holding out on us, and now we'll get to do all that stuff.
So just, build your use case. It still should solve some kind of problem, but, the problem can be arbitrarily
problem, my roommate is too calm in his room. Solution, the buzzer, which goes up at random intervals at 100
So
decibels.
let me just bring up the website not really quickly since it's our website, but so basically we have some details. In the end, you can build whatever you want.
So the one thing that we're constraining you to is that we are going to give you a set of 3 microcontrollers to choose from. So before, we told you you have to use the AT-Tiny. This time, we're going to introduce a couple of different options, which are all Atmel series microcontrollers. They all use the same tool chain, but some have a few more features than others. And we'll be going over that in the next week or
The
so.
only reason is we like it when you guys start from our skeleton file because it makes it easier for us to know that you hooked up the ISP correctly and that you're going to be able to reprogram your microcontroller. That kind of is a big deal when you're going to make a reprogrammable gadget. And that's what we're going to give you. For the Arduino, I mean, in general, we'll give you some links, but you can go find any Arduino. There are, I think, 37 different kinds by now. And you can use that as your reference. And I think we'll do the AT-Tiny, the AT-Mega, and the ATX Mega. That should be good enough for most people. You can talk to us, you can find something else, but in general, those 3 are going to keep you busy for quite a while. For the library parts, you're still welcome to use the Gadget 1 stuff. As you know, it's okay. So far we've only noticed one problem with the Gadget library, which was the wrong LED in the circuit. We'll find out what else we got wrong. So it's actually going to end up being on you for Gadget 2 to make sure that everything you use is right. And the worst thing that happens is it's wrong. You have to do something, substitute a part, and cut some traces. It's not the end of the world. And you'll either find parts online, which we're going to, we talked about on Monday, or you make them yourself. And either way, you want to verify them. Some I trust more than others. Unfortunately, Eagle is used by a lot of hobbyists, and anybody can sort of upload these random libraries. Some end up on Eagle's website, some end up on forums or the Arduino forums, and it's great because chances are somebody's already made the part you want. And if you're lucky,
They even made it correctly.
they made it correctly, but ultimately it's your problem. I certainly, one of the Altium, I think the Atmel, one of the Atmel libraries on Eagle's website, two of the pins were flipped. And I was just in there, and I verified it and checked, and I said, they got those pins backwards. Let me fix that. And of course, I didn't go back to Eagle's website and re-upload this corrected file. I just have my own fixed copy. So you have to watch that stuff. And you have to use at least one digital interface for your gadget so that we can say, yes, you used a digital interface. Here's your grade.
For most of you, if you're not interested in actually communicating with anything, adding just a debugging port that you can just print out stuff on will be sufficient.
And
So
that's
it's
fine.
an easy serial interface that everyone can do.
And it's actually surprisingly handy. So as you guys do your code for your sensors, you'll be like, I'm getting this sensor value. I sure wish I knew what it was.
Now's your chance to know what it
And
is.
it's very nice when you can just, even if you only temporarily do it while developing, you hook up serial to your computer, and then your gadget is simply telling you, hey, I'm reading this thermistor, the value is 137, just FYI. And then you can speed up your development. And then we're still going to sort of make sure you make nice compact boards, and then the PCB specifications.
So that's the details
Gadget
of the
1.
tracing, spacing. That'll just be from 33 each, since that's a good standard size that everyone can manufacture. Okay, so for this theme assignments, it's basically a use case similar to what you were doing for Gadget 1, a little more in depth, since you're probably going to have to specify some stuff that's non-standard that you want to use or things like that. But that's the idea. Explain it to us, and then the timeline going forward is we will look over those use cases, discuss them with you, and then April 5th, we're going to go through the schematic and layout draft, and then a week from then, we'll order those boards, and then get them back another week later, build them up, and on May 8th, you will be doing a final demo of your exciting gadget, which does something amazing, and wows
Generally
and
both
wows.
gadgets. I
Both
think we do an
gadgets.
open house, people from who knows where we tell people, and then they show up and you tell them about your
Yep,
gadgets.
so you get to present off your gadgets, show off your cool little things, what they do. It'll be nice, you get to see what everyone came up with, get to show off the cool thing you made.
Not a lot of time, it's about a week for your use case, so
Yep.
think about it.
So we have to go a little bit fast just because we have to order this stuff and get it back and have you guys assemble it, so.
If you want to stick around until, mid-June, we could stretch out the deadlines, but.
This is more for the, we don't plan on you guys sticking around after the semester ends than us. We're here forever, so.
And the only important detail that's different from how Gadget 1 was handed in, April 5th, we're really looking for a schematic and a layout. So think about both things. This is especially critical because you guys are designing the parts. And especially for Gadget 1, a lot of people just kind of said, oh, I'm going to use this part, this part, this part. Let me just find these random library parts and just throw them in my schematic. And like, the schematic looks okay, we can talk about it, but your layout is just, has nothing to do with reality. It's very important that you be thinking about your layout, the part selection, while designing your schematic. So you need to be thinking about those things at the same time. And then there's about a week where we can do the back and forth and run you through the steps to get something that actually is producible. All right, so that's Gadget 2. Yep, requirements.
Yeah, this is
make
basically
things.
what's on the website. All right, on to the actual
So,
lecture per se, informational content,
Yes.
digital communication.
So digital communication is important. We're going to talk about serial first. It's the most basic. Everything, in general, technically all of these are serial communication interfaces.
So basically, on Gadget 1, we kept you from digital communication, but digital communication is this general idea that we can signal things to each other using series of ones and zeros, in binary and so forth. And basically, for the purposes of microcontrollers, there are two major ways of doing digital communication. There's serial and then there's parallel information. And parallel is basically, I just put in n I/O lines and I make them either 1 or 0, and you just look at all of the I/O lines and get some value out of that. But that's taking up a ton of I/O lines, and unless you're going really fast or something, it's kind of a waste of your microcontroller because you're using all of your lines to just represent all of these bits at the same time. So what most modern communication interfaces use is serial communication. That is, I put in a series of ones and zeros over time. And there's a couple of standard ways of doing that microcontrollers support and that other peripheral devices support. So that's what we're going over today. And these should hopefully let you interface with a variety of different modules and sensors that use these same communication standards.
So the first is, I'm going to call this serial. This is like computer serial. You guys do not have serial ports on your computers anymore.
But you
Maybe
used to.
you remember dimly the good old beige boxes. They probably had at least one serial port on them. Nowadays, what we do is we either use a USB to serial cable, and in fact, the cable we gave you to charge your mini gadget, that's actually a USB to serial cable. So you have one already that you can use. We'll also talk about how you can mount a chip directly to your board that does USB to serial, and then you plug a USB cable into it. And so this, in general, you have very simple connections. You can have a receive line, a transmit line, and then you need a ground reference. Otherwise, it has no idea whether that receive or transmit line is high or low. And what this is the RX is for receiving. So if a computer or some other device is sending data to you, it comes in on your receive port. And then you transmit on your transmit line, and that goes to the other guy's receive port. Technically, you could have unidirectional serial where you only transmit to somebody or you only receive from somebody. A good example of this is like a GPS receiver. If you actually wanted to use a GPS receiver, it's super easy. It talks serial and it just outputs data. It just tells you where you are.
Yeah, so it doesn't have an RX line because it has nothing to receive. So it'll just have TX and ground, and then it'll just spew information at you as long as you like.
Yeah, so if you wanted to get your universal frame coordinates at any time, you can just look up a GPS receiver, read it over serial, and it just tells you. And maybe it it takes a couple of minutes after power up, but you can just get this information. Now, the most common type of serial is this point-to-point asynchronous serial. So they're dedicated lines. They're completely independent. So you could be sending to someone, and they could be sending to you, but you're not doing it at any particular time. So like, a good example of this is, let's say you have a serial port terminal open on your computer, and what you're looking at is just whatever the robot or your microcontroller is sending to you. So it could be saying, hey, here's my sensor value. It's 137. And then you programmed it to every second give you the new update. It says, hey, my sensor value is now 138. Hey, now it's 650. And you can just be getting this. And at the same time, you could be typing in key commands like S for change sensor ports, or C for blink the LED, or R for blink the LED in red. So these are happening at completely independent times, and you can do whatever you want with them. And the clock is asynchronous, so it doesn't trust that when you're receiving, the other guy has to be transmitting. For that, there's a different kind of serial. So the detail with serial, other than making sure that your receive line goes to his transmit and his transmit goes to your receive line, the other one as well. You have to, other than that, you also have to have the same baud rate because you have to agree on what your serial speed is. And these are all symbols or bits per second. It's not technically bytes per second, it's symbols per second. That's what a baud rate is, because there end up being a few extra details to it. And then usually they're all very common ones is 9600 to 115.200. If you've ever opened a serial port, your choices are generally some permutation between 9600 and 115.200. These are actually legacy. This is all based on a 3.46768 megahertz crystal, or some number like that, that everyone used back in the 80s. Whereas nowadays, people are running way faster, and you could easily just type in like 500 kilobaud or 1 megabaud. And generally the idea is just you have to get this decided ahead of time. So the biggest headache with serial when you're talking to a device you've never talked to before is, I wonder what baud rate it's at. So then you just start trying, like, is it 9600? I don't hear anything. How about 19200? No, still nothing. 38400? And you just keep cycling, and you're like, this is really annoying. I wish I knew what I programmed the baud rate to. And then once you've exhausted the list and tried all the weird ones, then you try flipping your RX and TX knobs to see that you didn't get those reversed. And then lastly, the only other detail with serial, especially nowadays, it used to be that serial was basically always RS-232.
Which is a standard. This is recommended standard 232. So basically the idea is that these manufacturers back in the 80s came up with what they thought were good standards for signaling. And what they wanted was the ability to go over really long cables and, basically have a lot of noise and stuff like that, because that's what they were doing. And so they wanted really big voltage swings, because if you have a long cable, this really big voltage swing is easy to detect on the other side. So they said, okay, let's use negative 15 volts and 0 volts as our 1 and our 0. And then there's another standard, RS-422, which is a differential standard, so it basically just looks for a difference between two voltage lines. And then these days, you can often just use TTL, which is just your basic normal digital I/O of you're either connected to your power, which is 5 volts or 3.3 volts, or to your ground, which is 0 volts. Now, with these two, basically you need to do some level shifting. You need to get a chip which converts from your TTL signal of 1s and 0s being 5 volts or 3.3 volts and ground 0 volts to some crazy like 15 volts or 0. But you just buy that chip and stick it on your board, and then it just magically creates these RX and TX lines that are at the right voltage and do the right thing. So basically, you need to figure out which one of these you need based on what you're connecting to, but then you just plop down the appropriate circuit on your board.
And so these are called transceivers when they take a signal and convert it from one standard to another. And in general, if you were talking to an external device that came in, actually has its own plastic housing, it's probably going to be talking RS-232, unless it specifically says 5 volt TTL or 3.3 volt TTL. If you were buying a chip from DigiKey, like an accelerometer or some other digital device, it almost always is going to have TTL. Usually, for board level stuff, everyone just uses TTL, and then only if you're going to go off board over wires of indeterminate length and quality, do you use a transceiver to some sort of noise immune system. Because I don't know if any of you have done a lot of breadboarding, but if you've ever done anything like serial, if you're talking at 9600 baud, you can basically get away with like protoboard wires or even coat hanger type stuff. But as you go faster and faster, everything gets uglier and uglier, and like the bits stop making it from one side of the wire to the other, and your serial doesn't work. And then you have to like do it properly with good cabling, and then some of the stuff works.
So once you're at like Ethernet speeds of hundreds of bits per second, you actually have to consider that there are bits that are in transit along the wire at a given time. Like they are a pulse that is traveling on the wire. You can have certain numbers of bits on the wire, as in just flying through the cable at like a foot per nanosecond or something like that. And that you have to think about that, because those bits, like as you're putting new bits on the wire, they're sort of traversing and causing.
Yeah, and these are sort of the details that we're running into now, because at some point, light only goes so fast, and we're starting to clock
Electrons
chips.
go close to that fast, yeah.
Our chips are going at the gigahertz, and sort of saying, well, if I'm going to put these two things 3 feet away, you have you have multiple signals on the same piece of wire, and that's very strange to think about. Because you have to start worrying about the time delay.
Yeah, luckily for your purposes, which is one of the reasons why we stick to these simple interfaces, you can have a magic module which will deal with all of that stuff and convert to one of these low-speed buses, which you don't have to think about all of those things for generally. So if you're communicating at even 115, 200 BPS, you really don't have to worry about that time it takes for bits to travel through traces and stuff. So that's a lot simpler to deal with, which is why we focus on that. And these days you can get a module which converts to this low-speed stuff just fine.
So, don't want to go on and on about the same thing anymore, but just make sure when you're planning your use case of what you're going to actually use, make sure you're aware that is it an RS-232 device, RS-422, RS-485, or is it a TTL voltage? So that, do you need an extra circuit, or can you just talk straight to it? So just to get into the nitty-gritty, so what actually happens, because you have no common clock, how do you detect when someone's sending you something? And the way it works is basically there's an encoding where the line is actually idling, and then suddenly a start bit appears. And what happens is that start bit is, it's going to be at whatever frequency you're at. So let's say, let me just say we're going to talk at 1 kilobaud, just so I can do that in my head. What that means is 1 kilobaud means that every symbol is going to take 1 millisecond, and it's going to be there for 1 millisecond. And the way it works is everybody who is going to have a baud rate, they actually are clocking at 8 or 16 times that speed. So they're actually checking this line at either 8 kilobaud or 16 kilobaud. And then what they're going to do is they're going to just kind of keep an eye out for a change to the start bit. And then once it sees the start bit, and it could be off by a couple clocks, it may not see it at exactly the same clock as when it started. And that's always the case because there's always electric details where the wire doesn't go from a 0 to 1 instantly, or in this case a 1 to 0. And then what it does is it detects it, and then what it does is it samples. It says, okay, I've detected a start bit. Now I'm going to kind of wait until what I think is the middle of that bit, when everything should be settled, and then I'm going to check again in 8 or 16 clock cycles to see what the next bit is. So we see a start bit, and we see actually that's a 1, 1, 0, 1, 0, 0, 1.
Yep, inverted logic, you might notice.
Yeah, RS-232, they use inverted logic just to annoy people. The 80s were a strange time.
Yeah, so basically, the important thing here is that this protocol is well known and everybody has sort of the same idea of what it should be, including your microcontroller. So when you're configuring to talk to a device using this type of serial, you don't have to deal with how this is actually coming in or even what exactly is going on. what you have to do is match up the settings that your microcontroller is using with the settings that the peripheral device is using. And so basically, the settings for this are including the baud rate. You also have to set how many bits are in the data section of each of these little packets, how many stop bits are being used, because you can use more than one, a check of parity, which is another bit which can be adjusted to check the validity of the data, and if you want to use flow control. Now back when modems were being used and stuff like that, flow control basically was a way of you signaling, like, I'm not ready for more data yet, like hold off, or I am ready for more data, you can send stuff to me. And these days, you don't really need it because your microcontroller can handle all the data and it's deterministic, so it'll always be able to handle all the data. So the most common settings by far are having 8 data bits, 1 stop bit, no parity, and no flow control. But this is stuff that is available in the data sheet of whatever you're talking to. It'll tell you flat out, like, I'm transmitting with 8 data bits and 1 stop bit and no parity. And it may have flow control that's optional or something like that, but usually they don't care.
And flow control actually requires additional pins and additional wires to
Yeah.
do it.
Flow
Which is
control
why
is-
most people don't do it.
It's literally 2 extra wires, and then if the wire is high, it means don't transmit, and if the other wire is high, it means the other guy's telling you that they're ready to receive.
And now this is actually where we go from symbols to bytes per second. So for instance, there's always 1 start bit, 8 data bits and 1 stop bit. That means for every 8 bits we send, we are sending 10 symbols. So when you want to calculate how many bytes per second we do, it's not 9,600 baud divided by 8 bits.
Because you have these extra couple of bits to signal starts and stops.
So it's actually 9.6 kilobytes per second. Or no.
It's a little less.
Yeah.
But anyway, the point is you're going to get a little bit less than what you think you should get because of these extra symbols. But that's basically how this is configured. So these end up mapping to registers that you configure on the UARTs of your microcontroller. And it'll just be in the data sheet, like, do you want 8 bits or do you want 10 bits? And you'll say, no, I want 8, 1 stop bit, etc. They're just bit flags, you set them right, and then it just sort of works. You get in.
And we're going to talk about this next week. Next week, we're going to do specific code examples. Here's how you use serial on a microcontroller. We just kind of want to do the high-level stuff so you know what's out there. This is used everywhere. 99% of what you will do, these are the settings. Only really annoying things, these different settings.
So say we wanted to send
I think
hello.
we covered this.
Yeah,
I
and
really
this-
want to look at it more.
This is for you guys to look at this PowerPoint if you want to look back and see exactly how stuff would be encoded. But this is basically, if we were sending hello, here are the actual bit tables that would be sent on the wire as a sequence, and the sequence of what happens on the sender and receiver. But it's basically just us running through the same exact sequence for H, E, L, L, and O as different.
And this is just ASCII, very handy for printout, and also half of the in-jokes in Futurama is in ASCII. So really, the only thing to worry about is make sure your TX goes to their RX. And it's have their
The
TX.
mistake is connecting the TXs together. Because both of the chips, when they say their TX line, is that's the line that they are trying to set to send data. And so if you connect them together, both of them are just going to try and wiggle this line, and both of them are going to look at the other line that no one's talking
And the
about.
way this used to work in the good old days is you'd actually have a null modem. You'd have your serial cable, and then you'd have a little dongle that's called a null modem, which basically just, all it did is it swapped the TX and RX lines, you could plug them in. And that's how you had to do multiplayer video games back in the early 90s.
Yeah, early 90s.
And it worked. And
I ran one all the way to
does
the
anyone
next
actually
neighbor's
possess
house
a null
once.
modem? Yeah, I think so.
Yeah.
You're not missing anything. These are wonderful things to get rid of. But on microcontrollers, right, on a 25-cent chip, you can now do what state-of-the-art, computers did, 20 years ago. And it's like, okay.
Yeah, the second most common issue is that you're actually talking on the wrong baud rate because you didn't read the data sheet or you forgot to set your settings correctly or some reason that you have.
And there's 2 possibilities. One is you just read the wrong thing. A lot of devices are configurable, and you might configure it to some faster speed and then forget you did that. And you're trying to factor in default settings.
And the second is that you have miscalculated how to set your baud rate because they don't necessarily say like, I would like to set this to 115, 200. They're like, how should I divide my clock? Basically,
Yeah.
that's
So
the
you
setting
have to
you
know
actually
what
set.
clock
And so
you
that
want.
depends on, are you running a 20 megahertz microcontroller or a 9 megahertz microcontroller? There's a little formula that you
There's
have
a
to solve.
formula, and for 18 megas and 18 tinies, they're a little tiny, you would just say, here's this giant table. What frequency are you running at? Set it to this bit. And like, you don't have to worry, because there's a little detail with the formula, which is, you do the formula, and then you might be dead on if you're doing something that's a fractional, because all these things are based on that weird 115/200, which is 1/16 of 3.4864, some, that crazy crystal I can never
That no
remember.
one has anymore.
No one uses them. Now people run at 8 megahertz, 16 megahertz, 200 megahertz. Nobody runs
Yeah,
it.
so you're never exactly on with your formula, and sometimes there are multiple ways of solving it that get you closer or further. So the long and short of it is, usually you just want to try and find these settings online somewhere or in a data sheet. It is very common to get them set wrong, even if you know what you're doing, just because it's a lot of fiddly
And you know,
bits.
you use the formula, you think you're clever, and then you end up being off by -3%. And it turns out that the other chip you're talking to got the formula off by +2%. So now you're off by 5% and it doesn't work. And you have to get it wrong in the right direction.
That is
XDs
less common these days.
XDs do that.
Okay, but it's less common in general.
Okay, so that's serial. But now we're going to talk about the serial peripheral interface. So what is this? Everything's serial.
So basically the idea is that serial came out of the need for two devices that are basically like running their own microcontrollers to talk to each other. Because they have their own clocks, they're doing their own thing, they want to communicate data to them. So it's asynchronous, and it's usually at these high voltage levels, so you can run it on a long cable. So now chip manufacturers are like, well, we want to run stuff too, but if I have a tiny little device, I don't want to have to like put a crystal in it that has to run and then run this asynchronous protocol. So a couple of new protocols spun out that basically don't require one of the chips to have its own clock. And these are synchronous serial interfaces. And one of them is SPI. So SPI is what's typically used for when you have a bunch of smaller dependent devices that are connecting to something like a microcontroller. So it's a lot simpler in terms of the implementation, but it uses more lines, and it's more designed for if you have two things on the same board really close to each other, and you want to talk between them really, really fast, and one of the devices is really simple.
Yeah, and the idea here is that one of the devices is basically always in charge. So you know, they have computer technology, they love master-slave terminology. That's basically what it is. Somebody's in charge, and the other people are not in charge. And whoever's in charge is in charge of either doing slave select, it's also called chip select. And what they do is you say, hey, I'm talking to you, and then you actually provide the clock. So they just have, and what this, if you're familiar with registers, what this literally is you have a register filled with data, and then the master gives you a clock, and you clock it out as a shift register. That's all it is you're shifting the data bits out, and the data comes out
At the
to
same
you.
speed as this clock. So
Yeah.
basically, you're saying, okay, you device, give me your data, and you wiggle the clock line, and it just says, oh, I'm getting clock here, have this data. And then basically, you can also send data, you can wiggle your clock and also wiggle out a data line, and the slave basically
And the
gets
nice
that
thing
into
is
its
that
register.
there's no confusion. The clock line is the same on both chips. The MOSI line is the same on both chips. The MISO line is the same on both
Because
chips.
both of them agree which side is the master and which side is the slave. And so you don't have to do any weird flipping of these lines. You don't have to do any weird clocking, or you just have to sort of get it within a range of whatever the device supports, which is usually really, really, really large. And so it's really nice for on board where you don't have to worry about these things. And it's really easy for manufacturers because they don't have to make a device that
Shift
runs a
registers
clock.
turn out to be really easy to design and implement and get right and describe. So that's why everyone likes it. And what's really nice about it is, you know, you say, well, that's a lot of lines to be using. What happens if I want to have 10 sensors that I need to read over SPI? I don't want to have 50 lines. Well, you don't actually have to. You just have to have these three, and then most devices that support SPI agree that when the chip select line is floating high, they do not touch anything. They don't do anything when the other lines are going. So they disable their outputs. And so what that means is if you have 10 sensors, you just have 10 different chip select lines, and you only talk to one at a time. And you get to pick which one. It's not hodgepodge and insanity. And you can clock at whatever speed you want. And you just make sure it's either not too fast for your device, but in reality, nowadays, your microcontroller is going to be the slowest thing on the SPI bus. So it's great because you don't have to figure out the baud rate. There's no clock skew unless you're on like 10-foot wires. You know, they go super fast. Your things can go 8 megahertz. So like if you're talking to like a memory chip and you want to store a whole bunch of memory, that memory chip can go faster than you possibly could. And you know, and what's really interesting is that you can actually, if you're manually clocking it, you can just pause halfway, you know, do something else for a while, and then continue clocking it later. Nothing happens. It generally just works. Now the detail is that you have to know about the data format.
So unlike the previous computer serial, this spec really only defines those lines. It doesn't really define how data is passed along those lines. And so different manufacturers have different ideas as to whether a high means a 1 or a 0. They have different ideas as to sort of how long the register blocks are, although they're usually 8 bits. They have different ideas as to if you're sending something that's 4 bytes as to whether the most significant or least significant byte
Bits
are. Right, that's true. So basically, you have to figure out what the person on the other end is actually going to send you in terms of the actual byte or bits that you receive.
You don't necessarily have to understand what's going on here, but in the data sheet it tells you this is what we do, and then you make the Atmel chip match what it's doing.
Yes, once again, the Atmel chips are very nice, and most microcontrollers are, in that they have settings to deal with all of this. They can automatically flip the bits, they can automatically read in different block sizes. In hardware, you just have to tell them what you want them to do. And so, once again, registers, you set them, and then everything will just sort of go.
And you do have to make sure your voltages are compatible or tolerant. There's no RS-232 for SPI, but what you'll frequently have is your microcontroller, if it's running at 5 volts, you do not want to talk to a 3-volt SPI chip because you will blow up its...
Unless it says it's tolerant.
It may say
which
5-volt
some are.
tolerant.
Yeah.
And you may find that like a lot of very cool chips, like tiny accelerometers that cost $1 and do everything, make you breakfast. They're 1.8 volt devices, but they're 3.3 volt tolerant. So then you say, well, should I be using 5 volts on my microcontroller? The answer is no, not without additional circuitry to interface. So that's just, you keep that in mind for when you pick what your VCC should be.
Okay, so here's an example of what's going on all of these lines when we're doing an SPI transfer of data. So one thing that's kind of interesting is that really you can actually have data going both ways on the same select and clock cycle, but of course, usually you have to specify something ahead
So
of
what
time.
this is, just to give you the high level, for most SPI devices, the most common way to interface to them is first you select them, then you give them some sort of command and maybe some data, and then what you do is you just start clocking out zeros.
Whatever, yeah.
It no longer matters, you're just running the clock, and then they answer your command. So
All
one
the
common
same.
example might be temperature, crazy sensor, give me your temperature. And then once you've told it that, the next thing it does is it gives you its temperature.
And you're actually providing these 3 lines. You're doing the chip select, and you're actually running the clock. Even when that guy's sending to you, you're providing him the clock that he's using to send you bytes. And so you have to make sure that you're actually doing that long enough for him to send all the bytes that you're interested in.
But it's actually very simple. You set this pin low. So in your code, what it ends up looking like is start transaction. Data byte 0 is blocked. Wait, byte 0 and 1 is blocked. Byte 3. And then you just keep reading until you have all the data you want. And when you're done, you just set the pin high again. And you're done with that chip. And then you move on to the next chip or the next chip. And you generally set it high. Even if the next thing you want to do is talk to this chip, you frequently set this high again because that resets the little state machine. So basically, a little organ grinder, a little top goes the weasel sort of thing, where you just turn the cranks, you get the data you want, you reset the thing, and then you do it all over again. So when you start getting into the awful details,
Yeah, so here's where you
we'll
have to
talk
sort of
about
match stuff up.
briefly,
Well, we can
but
talk about it in
basically-
more detail, yeah. Basically, you can either sample on the leading edges of clocks or the falling edges of clocks, and you can either sample things with inverted logic or uninverted logic, and different manufacturers will say basically like, we set our bits out, like we set the value of them on the falling edge of the clock. And so you say, well, I'll read on the rising edge, which would be right in the middle of a bit where it's really stable. And you'll see lots of diagrams like this in the data sheet that sort of tell you, okay, you know, on the falling edge of the clock, that's right in the middle of where this data bit is set. So that's what I want. And they'll tell you, you know, whether they are inverting their logic on the lines.
So it's a little kind of awful to look at, and in general, like kind of beyond the scope of what we want you to do in this class. But just be aware this exists. In reality, when you're actually writing this code, there are 4 modes. There's mode 0, mode 1, mode 2, and mode 3. Usually, everyone uses mode 0 or mode 3. You try one or the other. If that doesn't work, try mode 1 or try mode 2. One of them is going to start giving you the right data.
Yep. Thankfully, you don't have a million baud rate configurations or clock dividers or anything. You just have to work out these
We'll give you a hand if you're having trouble with this, but generally, you just have to figure out which one it is. Your code will start reading it, and then you're good to go.
And other than getting gibberish, there's no real harm in trying the wrong mode.
Yeah.
It just reads gibberish or writes gibberish.
But basically, at some point, you get to where you can look at these super thrilling things and say, aha, I should be doing this. And yeah, we'll help you along with that if you need to use us beyond these gadgets. And if you're lucky, someone will just say, oh, somewhere in the data sheet will be like, hey, we use little endian and we're mode 3. And you say, great, now I just have to type that in and it works. Okay, so the last super thrilling
Serial
interface that everybody uses, especially for these small embedded things that you guys are building, is I2C, which is the integrated circuit bus.
So I think this was Texas Instruments?
Philips, I think?
Philips? Okay, Philips.
Uh,
Philips was like, we want a bus that's a serial protocol that we can put multiple devices on and not have to use a bunch of different clock select lines. They can all share the same transmit and receive lines, so they made a slightly more complicated protocol, so they wouldn't have to run all these extra
And
select lines.
very important, this is a bus. And what that means is you can basically have multiple masters. Other people can be in charge. It's not just somebody's in charge, everybody else does whatever it tells it to. There can be multiple things in charge querying the same thing. And so what that means is there has to be arbitration, there has to be addressability, all kinds of shenanigans. Now, you'll never find the word I2C in your AtMel data sheets, and that's because that's a trademark. You have to pay a license. However, many people often implement 2-wire serial or TWI, because they have very identical formats, but it's not licensed.
So you can see here that there's just these 3 lines, and you can put 10 devices, and they all share these 3 lines, and that's what that extra complexity is letting you do.
Now, for I2C, this is becoming less true over time, but there's a few fixed speeds that are defined in hardware. You either support low speed or high speed, and I think now there's super high speed, just to keep things complicated. The data format and the arbitration are hardware defined. You don't have a choice. What happens is this is an open drain system, and basically what that means is everybody can pull something low, but when they let go, it floats back up to some other, to the voltage.
And they have no mechanism for driving anything high.
And the reason for that is, let's say you have 2 things that are fighting with each other. If you hook up 2 transmit lines of microcontrollers to each other, you can do bad things where one of them is overpowering the other, and the other one is forced to accept current, and you may blow the thing up. And that's bad. So the way they work around that is they make sure that everybody can only sync current. And that way, when 2 people try to take control of the bus and sync current at the same time, nothing bad happens to the chips. And then there's details where, and so what happens is there's pull-up resistors to make it work. And it's kind of flimsy. I2C is my least favorite of the protocols, because it's kind of flimsy. It's meant for a PCB. You have to like, if you have problems, you have to like change the resistance values. If you're trying to run like long wires to some sensor that talks I2C, you can have problems with wires that are just too long. You got to do something funny.
Yeah, because it's open drain, setting this resistor or set of resistors that pull everything up is really important, because if it's too high of a resistance, then essentially when you drain it, it'll take a while to float back up, and that can cause problems. And if it's too big, then you might have problems draining it in the first place over a really long wire length.
And then usually what's nice is that they're all open drain, usually compatible voltages. They're almost always 5 volt tolerant, even if they're 1.8 volt devices, just because it's super easy to do that.
Yep. Since all they're doing is seeking current, they just have a little switch. They don't really care what the voltage of the bus is.
And what's really nice about it is these can be very small devices. They only need 4 lines, power, ground, and then these 2 data lines. So you end up with very small devices. And it's just, you want to use them on a PCB. If you're running 6-foot wires to them, you may have problems.
Oh, that got washed out a bit.
Yeah. Well, anyway, here's microcontroller, and here's 3 random devices.
Yep, and they're all sharing the same 2 transmit receive lines, and you can see the pull-up resistors here, which are shared for all of them.
Yeah. And you can have like 100 things on here. So like if you're really cramped for space, you're like, man, I really want to have all these crazy sensors, but I only have like a small chip with not a lot of pins because I have a small board. Here you go. This is how you have a million things at the board. And then I don't want to get too much into the I2C specification, but basically, like SPI, you want to be able to write commands and then also read data. And the way they do that is, of these 8 bits, one of them is special. The bottom bit is special, and it either means I'm sending you a write command or I'm sending you a read command. So it's another way where they do very simple bidirectional kind of stuff. And that's why there's only, technically there should be 127 unique addresses, but there's a couple for like I2C extended mode, so like that goes away. But I don't want to get into that. But anyway, you can have a lot. And then, let's see, we got a couple magic states. And then there's arbitration. There's almost always hardware arbitration. You only run into this if you're trying to implement I2C in software. And then you have to implement all these features. But all of your ML chips generally have I2C.
Yep, as TWI.
Yeah. So let's...
And a lot of the time, you don't have to worry about this, because in most of the circuits that you're doing, your microcontroller is always going to be the single master on the bus. And all of the other devices are going to be not masters. So it's usually fine to just use some of the more common master modes available in TWI. You don't have to do crazy multi-master stuff most of the time.
Yeah, don't do it. One nice thing about I2C is when you send 8 bits of data to your other device, they actually will do a pulse on the 9th bit and just see what happens. And then you can actually know whether someone's actually listening to you. Whereas SPI, you can be clocking for days and you never know if you get zeros because the other device is saying 0, or if it's dead, someone forgot to solder it in. You don't know. Whereas I2C, you send them a command or some request, and if they don't respond to you, you know they didn't respond to you. So it's kind of a nice sort of positive response. And there's some box scratching. If you're implementing your own I2C slave, you could break the whole I2C bus. Usually people who sell things don't. So being an I2C master is very easy on that ML chip. I don't recommend being an I2C slave though. So in terms of what actually happens, it's not too bad. The master waits for the bus to be idle, and if you're the only master, it's pretty easy. And then what you do is you start a command, then you write an address, you would maybe write a command like, hey, give me your temperature, and then you would issue a restart, write to the same address with a read, and then read a data byte. And then in theory, you just got the temperature byte. Or if it's 2 bytes, you read 2 bytes in a row. And then you would do an I2C stop. And that lets go of the bus and resets the transaction.
And you can see that what's going on here is very similar to what's going on in SPI, except that both the master and slave are sharing the same bus for data signaling. And they just have this protocol in place for them not to be writing at the same time.
And so if you look, it's a little bit more work than the SPI example where you're just like, I'm going to start this transaction, here's the commands I want, and now I'm just going to keep reading, and the data bytes I want are going to come back. Whereas here you have to write some commands, restart the bus, read the stuff. So it's a little bit more work. And that's the most common way it's used. You can eventually, what you often do is you set up the I2C device with some write commands, and then every time you read from it, it gives you the data you want, just to simplify this, because this is kind of a little bit of work. The code ends up being pretty short, but it's a little tedious. So yeah, APR master code is pretty easy. We're going to talk about that next week. In terms of devices, most have a single hard-coded address. So if you want to buy a temperature sensor from DigiKey, you can get these super tiny things with like 3 or 4 pins, but they only have one address. And they'll say, my address is number 37. And that's great until you want to say, well, gee, what if I want the temperature over here and over here? They both have address 37. You can't use that chip. Or you get unlucky and somebody else's accelerometer also uses 37, which is super annoying. So what frequently happens is you have these chips where it really could be a 4-pin chip, but they end up having 8 or 16 pins just so that you can set some high, low set pins just so it has a different address.
Yeah.
So it'll say, I'm going to be 37 plus some offset based on whatever you set on these little dip switches. And you're good to go. And so sometimes like temperature sensors will be like, oh, this temperature sensor can have 8 unique values. This one can have 16 unique values. And that's how you pick which one you want based on how many they're unique. And in general, really what you do is you see if it works. Just put it on your board and see if it works. But sometimes you might have to see what you're actually looking for is when you turn off your 0, you want to go back to 1 real fast. But if your pull-up resistor is too high for some reason, you're going to have this sort of gentle return to 1, and that's not going to work. And you just lower your resistance. It's as simple as that. But nowadays, things are a lot better about that. And it actually gives lower and lower values. Okay, so that's sort of the fun with the 3 big serial interfaces.
So those are the protocols that you will actually probably use on those microcontrollers. There are newer ones that directly support more advanced protocols, but those protocols tend to be more complicated. And some of them are up here. Now, the point is that these protocols, like USB and various forms of wireless, usually there are commercial modules available which convert from these protocols to one of the 3 that we just discussed. And for the most part, unless you are really happy writing 10,000 lines of USB driver code or cross-compiling a wireless driver stack, this is a lot easier for most people. And these modules are not too expensive these days.
Yeah. And there's details like, so for instance, the Ethernet interface, the back specification, that is actually not a free document. You have to spend like $1,000 to purchase a licensed copy of the Ethernet specification. Obviously, there are billions of Ethernet devices. I guarantee you that most of those engineers who implemented them didn't purchase or look at this document. And you could do the same. It's just, you're sort of getting into where like professional engineering is like this, developing this stuff constantly. Wi-Fi. I mean, how many Wi-Fis have we had in the last 6 years? Keeping up to date with all this stuff is tricky. And same with USB. You can now buy Atmel chips that directly support USB, but it's a much more complicated and sophisticated protocol. And that's how, an Atmel chip could be in this mouse, or it could be in a laser, it could be in all kinds of things. And we're not going to get into how you design USB peripherals for computers.
But what you can all do is buy a USB serial cable or USB serial chip and just stick it on your board. And that's just a chip and then like 4 capacitors. And then it talks serial, and you guys can do serial really easily with a couple of lines of code. So we highly recommend doing that, but you do have the ability to use these other interfaces which you may be familiar with.
So we're not going to stop you if you desperately want to do USB stack implementations on the next mega, but
We are going to help
you're going to help you. We're not gonna-
Yeah.
Whereas if you want to talk serial to a computer, USB to serial, great.
Why would you want to directly use these? Is there any advantage to?
Yeah, so there's a number of direct advantages to using it. USB is much more common on a computer than a serial port is these days. So if you want to have a device which can plug straight into a computer and can talk to software on it, a USB serial converter is a really good way to go, because then people don't need special software. You just plug it in, and Windows, Mac, and Linux all know how to recognize the standard chips. So
Now,
that's nice.
there is sort of a cost complexity.
Yeah.
That chip is $5, and it's there because it's really convenient for $5. So their price has not changed in 5 years.
Yeah, but that's a trade-off.
And they have good driver support.
Yeah.
There are other USB serial adapters and chips that we are never going to recommend to you because they have terrible drivers.
Yep. And so for using wireless, the reason there is pretty obvious. If you want to communicate data off of your device without using a wire, you're going to have to use some sort of wireless module.
I meant like directly as opposed to
Yeah,
using
so
this.
if
Oh,
you
using it
directly
directly,
use
okay.
USB,
Well, you can directly use all of
you're
it.
not, so code-wise, in terms of software on your computer, to talk to a USB to serial adapter, you just have to open a serial port.
Okay,
It's
so
crufty and old,
I
but direct USB HID.
Yeah, so
you can do.
the reason that you want to use one of these directly is because you want to use parts of the protocol that are not available through a conversion, or because you want to do it really, really fast, or because you want to use fewer parts. So for example, USB, like USB 3.0, I don't even know, what is it, like a gigabit or something like that? It's crazy fast,
It's
right?
just PCI Express.
Yeah, well, it's really, really fast. It's much faster than you would be able to run a serial like RS-232 or possibly even SPI. Well, probably not SPI. But the point is that if you have a direct connection to your microcontroller, you can probably push a lot more data through it. The cost is that you have to implement a USB driver, which is usually like a couple thousand lines of code to get everything sorted out. Usually you can find it online and modify it or something, like Loofah and stuff. But
Yeah.
anyway, the point is the code is a lot more complex, but you can do fancy stuff like then you can enumerate as a keyboard, or you can enumerate as like a flash drive, right? Which you can't do with a USB serial module. That will only give you a serial port. Similarly, with wireless, you can, if you're directly doing it, you can do all sorts of stuff like via router or run a mesh network or things like that. Now modules aren't going to support that. They're just going to be like, okay, here's how you send data, and here you can set an address and like stream packets out or whatever, which is often all you really care about doing. So that's the trade-off, is you are trading off all of the full functionality of these protocols for a small subset, and you're paying a little extra money for these modules at $5 to $10. But the upside is that it's a lot simpler to use those modules in your software and in your layout.
So if you wanted to build a USB mass storage device, probably that's more like grad level ECE class in systems engineering. And you have, this is where like the example is the code gets worse and worse, the documentation gets worse and worse, and you're like kind of these bare metal USB stacks. Like if you have to implement a stack on your embedded system is much more complicated.
So Brian and I recently did an Ethernet to a microprocessor, a little bit bigger than what you guys are using. How long did that take us? That was
Well, even using other people's drivers, in theory, their code should have just worked. But then rounding out those details took a couple of weeks
yeah,
of just figuring out what was wrong with our implementation that was slightly different from their
between
implementation.
both of us, and it turned out that we were using a 3-port switch chip, and we were selecting the
We're
wrong.
talking to the wrong
We were
part.
talking to the wrong physical transceiver on it. And
So there's just this sophistication, right? Serial is really simple. It's been around since the 80s. It was state of the art in the 80s, but now it's pretty easy to wrap your head around. And everything else has gotten more and more complicated. Like USB is kind of complicated, but not really because there are these standard profiles. Wi-Fi is
crazy complicated.
And every new version of Wi-Fi that gets more and more sophisticated so that you can stream, real-time video, in your bathroom, in your house from a router, it's like, that's hard to do. There's a lot of engineering that just keeps changing constantly, right? I don't even want to know what the next wireless standards are.
Yeah.
Bluetooth is the same. They keep trying to fix it so that people's phones don't keep dropping out with their,
Headsets.
because they don't care what's going on, right? No one cares. They just want it to work. And people will basically beat at these things until it works. And Zigbee, right? It's being rebranded for basically a low energy. Mesh
So anyway,
network.
these protocols are nice if you want to talk to other stuff and not need people that have special hardware, and you can do it with these modules.
So rather than implement USB. You can just get an off-board USB serial adapter, super easy. The one you would have was like $8 from your
Yep,
mini
so if you
gadget.
guys
You
look
already
at
have
the mini gadget schematic, you can see one of these on there. Or did we do it in the cable?
It's the cable.
It's in the cable. Okay, so if you look at the part for your mini gadget cable, that part actually, the cable itself includes a USB serial converter. And so the chip on the mini gadget just sort of talks TTL serial out to this cable, and in the cable it gets converted to USB.
And you can put it on your board if you want it a little prettier, because then you can plug a USB cable into your board instead of this special cable. That can be nice. And then it shows up as USB to serial adapter. But some will let you do special API driver calls and like via mouse instead. And the FTDI is generally, I'd say, the best software support. There is trickery possible using things like eUSB, where someone has basically, you can like get this and like mess with it and like on your tiny microcontroller, your USB peripheral. But it's ugly and complicated. If you want to do something else, like 80% of your processor is busy doing USB. And if you're lucky, you can sneak in your 2 or 3 sensors without breaking the USB thing. And if you break it, I'm not helping you fix it. That's why we recommend just serial. Serial is super easy, very handy. Same with these. So these are all there. See the word serial just keeps coming up. It's like Zigbee, you can get like direct things. You can get SPI, Zigbee adapters, but serial is just so much easier. So like roaming networks does a lot of these embedded modules. There may be other ones. I don't look too often. Where like, you want to talk Bluetooth, here you go, here's the RM41.
You just stick it on your board, and then you just sort of like talk to it and be like, hey, could you send this data out for me? And it's like, no problem, I'll send it on Bluetooth for you.
And you know, here's the like, what is this, $20 for an RM41?
It's like 14 bucks.
14. I found an $8 one on Deal Extreme, which ships straight from Hong Kong. You know, maybe it's as good, maybe it's not, I don't know. You know, but you know, when people are talking about Arduino stuff, sort of nice that right now, if you search for whatever protocol you want to talk, and you add the word Arduino, chances are somebody sells in a blah to serial adapter, and somebody has Arduino example code. So like if an Arduino works with it, then you know you probably can get it working too. Especially with all that stuff open source. Zigbee, I don't know that you can use it, it's cheap.
I guess the one time you use Zigbee is useful if you have a bunch of little gadgets that you want to talk to each other. Because unlike Bluetooth or Wi-Fi, Zigbee's just like an open networking protocol. So like there's no control over it. When you send out a Zigbee packet, like all the other Zigbee radios in the area just get that packet as long as they're on the same network name as you. So if you want a lot of gadgets that are talking to each other, Zigbee's a good option. Bluetooth, you need to have some sort of host device. Wi-Fi, you need some sort of router, stuff like that. Zigbee, you
It's
just...
good for just mesh networks. This is actually what it was used for. Also, the range on Zigbee is great. Like, if you wanted a 1 mile range, because you're going to have these sensors out in the fields, Zigbee has 1 mile, and you can get more than this.
It works okay.
It works okay.
It works. It's better than Bluetooth.
And Bluetooth is, you know,
better
10
than
meter
Wi-Fi.
plus or minus, whatever that wall is in between you. So you can do this wireless stuff. It's not too bad. And just, you want to look for a module. You can do whatever you want, but I strongly recommend doing a serial module. Only because, you know, for this class, we don't want to force you to make, you know, software stacks. It's just not worth the time. You're not trying to save $8 on a million count, you know, by implementing it yourself. That's basically it for the miscellaneous.
So welcome to digital interfaces.
So here's just sort of the high level, get thinking about it. When you're looking for, you know, a device that you're going to shoehorn into Gadget 2 to meet your minimum qualifications, you know, think about what you want to do and you know, what you want to play with. Because you're going to have to go out and find this stuff. And then next week we're going to talk about specifically how you implement this stuff. Serial is pretty easy. SPI is pretty easy. I2C is also pretty easy.
Pretty easy.
It's very straightforward. Whether or not it works for you is another question.
So yeah, I think at the end of class, we'll spend the rest of the time answering questions people have about their gadget boards and stuff like that. So.
All right. Any Gadget 2 questions? All right. Like that.
No, but give me 2 seconds. I'll show me where the